Hello. So I made a decision. Until it works, I'm going to do it every lecture once. So you may see it again and again. So while watching what's going to happen, it's all been charged already, you know, the ball's inside. This is the question about the current topic. Also, I have an announcement. Just like 5 minutes ago, I finished correcting the grades based on your emails to me, attendance and lab and discussion grades. And this, how many requests I had. So there's a chance that I might have missed one or two. So now it's ball on your side. Now you should find the time, check your grades, see if what you sent has been done. If you see any issue, send me an email. But I wouldn't expect now so many. Attendance, lab grade, discussion grade. If you've sent me an email about that, that should be fixed. Well, and so now I'm going to switch. Keep pressing, please. How do I do that? Ta-da. Ta-da. Well, this is the question. If you didn't answer yet, go to the answers. 1, 2, 3, 4, 5. Maybe bigger scissor helps, I don't know. It does. What? I told you last time it's going to be loud, and when I held scissors in my hand, you should know what should happen. That's what physics is about. See? It is actually really, really powerful. So, well, good news, it worked. Bad news, you're not going to see it anymore. See? It did work. All right. Nothing left excited in life. So I'm going to take this over there. In fact, right after the class last time, I have a witness, yeah. I made a really good shot. This is what would give me the membership in NRA. Let's see. 73% students have answered correctly, but 27 are not. So this is what we call a phase transition. We have, well, several possible phase transitions which might happen. Melting is one of those. Freezing is the opposite to melting, also a phase transition, etc., etc. When phase transition happens, temperature does not change. We must remember that. So I didn't finish this problem. I'm going to do it very quickly. So again, it's not about the problem per se, it's about the strategy. Every time we have to ask the same questions starting from lecture 1 to now. What objects are involved? What processes are happening? What physical variables should be used to describe the properties of those objects and processes? How can we demonstrate what's happening visually using a picture or a diagram or a graph? And finally, what equations can we use? And only then, basically, physics is done and mathematics starts. This is related to the temperature. So it doesn't make much sense to use a Hooke's law. It has nothing to do to this. Or applying equation for the period of simple harmonic motion. No, it's about temperature. So we should ask what kind of a process might happen. Well, when temperature changes or doesn't change, when heat exchange is happening. So it's all related to what might happen to the heat and what might happen to the object. What might happen to an object? We have only two choices to answer that question: change temperature or change phase. That's it. Never at the same time. So any object either changes temperature or changes phase. So it's either or. And for this situation, we have one equation we can use for the amount of heat, and for changing phase, we have another equation. So lead, well, again, the temperature time, seconds, degrees of Celsius. The temperature starts at a certain value and it rises. And again, we have only two options: it reaching the melting temperature or it's not. So let's say this is the melting temperature. The melting temperature, 327. If the amount of heat is not enough to heat it up to the melting temperature, only one process happening, temperature change. If the amount of heat is larger than this value, the bullet starts melting. We actually can figure out that critical amount of heat. The critical amount of heat has to be equal to what? It has to be equal to the specific heat of lead, the mass of the object, and that temperature difference between the melting temperature, critical temperature, melting, and the initial temperature. This is the critical amount of heat. In this situation, we can see the actual amount of heat is less than critical. So the final temperature will be below that melting temperature. And what do we have to do? Well, as we said, because of the friction, internal friction, external friction, neglecting any energy loss to air or to the target, all kinetic energy of the bullet should be transferred into that amount of heat. So mv squared divided by 2 should be equal to the specific heat of lead times the mass of the bullet times the final temperature minus initial temperature. Question: do we have to use Celsius or Kelvins? Someone should say something. It doesn't matter. Because if the temperature itself in Celsius differs from the temperature in Kelvin, bless you, but please do it away from me, in a different direction. Make them sick, not me. I already have my... So the change in temperature is the same. that's very convenient fact. First of all, in this particular situation, we actually can even cancel the mass. So what's left? V squared divided by 2 times C plus initial temperature should be equal to the final temperature. Well, 100 squared 2 times. Okay, so if you look up any specific heat or latent heat of fusion, you may see many different weird units. For example, this is just a copy from one Google page, and it says joules per gram per Kelvin. So, well, in this situation, of course, we have to use kilograms. So that's going to be equal to 128 joules per kilogram. And there's an additional question. So how much heat will we need to spend in order to melt that bullet completely? Well, so now two processes should happen. It starts from some initial temperature. It's reaching the melting temperature. We know the melting must happen only at the specific temperature. That's the first stage. Second stage is melting. So for this stage, there's one specific amount of heat which has to be spent, and for this stage, there's another specific amount of heat which has to be spent, and a total amount of total should be first plus second. That's it. This is that critical amount of heat, which equals to the specific heat of lead times the mass of the bullet times, now this melting temperature, 327 Celsius, yes, minus 20 Celsius plus, and that, well, it has to be equal to the latent heat times the mass. So this is again 128 joules per kilogram Kelvin. This is 10 grams, so 0.01 kilograms. And here the same mass, well, latent heat times mass, 0.01, 10 grams. And this again is a number we just have to look up. Again, you see, that's a very weird unit, kJ. So what does it mean? Kilojoules per kilogram. So we cannot use 22.4. We have to use 22.4 times 1,000 joules per kilogram. So 22.4, 10 to the third. Well, let's put them all together. 128.01. 327 minus 20 plus 22.4, 1,000.01 joules. So this is the crucial part of the analysis. The rest is just plugging in numbers, using correct units. Another example. Well, that requires another question to you. So in the problem, I will read it again very soon, but what was happening? We had a container insulated from the environment, filled up with some liquid, let's say it's water. Can you tell me something about the temperature of this, well, let's say it's water. Any information about the temperature of water? If it's liquid, it's above 0 Celsius, but below 100, or it's above 32 Fahrenheit, but below 212. That's for sure. And we place in it a hot piece of lead. Lead actually is very common material for experiments like that. It has a relatively, well, its shape, first of all, but also values for specific heat, for latent heat. Good. So, and, well, in 5 seconds, I'm going to stop collecting your answers. 1, 2, 3, 4, 5. Well, definitely can't do this. So basically, we have to choose between this and this. And theoretically, it could have started boiling sometime after. Yeah, but immediately after we bring these two objects into the contact, yes, it's warming up. But again, theoretically, if the piece of lead is really, really hot, it might give away so much heat that first water warms up, reaching critical temperature, and then starts boiling. So it also could have happened. Now, this is the problem. So, what do we know? Liquid has initial temperature, T initial liquid, 500 degrees of Celsius. The solid lead initial is twice and twice means what? 1000 degrees of Celsius. That's the initial temperature of the solid object. So the mass of the solid object has 1/3 of the mass of this liquid. What do I do right now? How do we call this process? That's a specific mental process which is happening right now in everybody's mind. What's the name of that process? Any guess would do. Can't hear you. Analyze is the process which covers everything. This is a specific part of that process we call analyze. We're doing specific action, mental action. From the language of words into language of symbols. What do we do? From one language into another language? Translate. That's it. We're doing a translation from a textual representation of this physical situation into the symbolic. So let's keep translating. So this is done. Specific heat. Its, so the solid has, and its, so solid, twice specific heat of liquid. So translation has been done. Find the final temperature of this system. Well, we know eventually the thermal equilibrium has to be reached, and for the thermal equilibrium, we just have to write the heat balance equation. In this situation, only two processes are happening. The initially hot object cooling down, the initially cooler object warming up, no phase transition. Phase transition doesn't happen. So C solid, M solid, T final solid minus T initial solid has to be equal to C liquid, mass of the liquid, final temperature of the liquid, minus initial temperature of the liquid. What do I want? So this looks like this, but I have to use absolute values, and I'm going to use absolute values. So we have only two processes, so it's kind of natural to say the magnitude, the amount of heat released has the same magnitude of the amount of heat absorbed. That's it, two terms. Well, of course, we could have written it differently. Okay. T final, T initial minus, plus liquid, don't rush. That's for myself. Liquid equals 0. Mathematically, that's identical expressions. Now, here, what do we know? First, with specific heat of the solid object can be replaced with this. Now, the mass of the solid object can be replaced with this. Now, the solid object was hotter, so its temperature decreasing. If I want to get rid of the absolute value to make it positive, this is what I should write. The initial temperature of the solid minus the final temperature. And now I don't have to write that symbol solid because we know the final temperature has to be the same. They have reached thermal equilibrium. And that also should be equal to this times final temperature minus 500 down. So we can cancel those unknowns variables, and we end up with only one equation, which have to solve for only one unknown. Do it at home as a practice exercise in algebra, please. All right, so these are just standard values which we use in a classroom when we solve a problem related to phase transition of water. So actual values, you see, accurate values, slightly different, but here I'm going to use the approximations just to simplify calculations. Well, okay, you need to make an ice cubes. If you make an ice cubes from water, what do you have to do? How much heat should water. And if water cools down and it's freezing, it's given away. So water releasing the energy in this situation. So let's solve it. Again, we start from counting processes. So we start from water, and we put it into the freezer. What is happening first? First, its temperature goes down from 25 degrees of Celsius to what temperature? 0. It must reach critical temperature first. And there is a certain amount of heat related to this process. Released by water, absorbed by what? By the freezer. And then the second process is happening. We call it freezing up. And that process happens at constant temperature at the critical temperature. And of course, there's another amount of heat being released until water completely frozen. And then, now ice keeps cooling down, finally reaching the temperature of -5 degrees of Celsius, Q3. So, how much heat should be released in general, totally? Normally, we would expect a positive number. So we say it's released so much of joules. So basically, Q total is the magnitude of Q1 plus Q2 plus Q3. Each Q is negative, right? And all we need to do is just write down now an expression for each Q. First, we have water. How much water do we have? So we want to make 20 ice cubes, 5 grams each. 20 times 5, 100 grams of water should be used. 100 grams is 0.1 of a kilogram. For water, the specific heat, well, my simplified number is 4,000. Now I'm calculating the magnitude of this temperature difference. It should be 0 minus 25. Okay, that's a 5, not an S, 5. Plus, next term, water freezing up into ice. This is the latent heat we have to use. 3 times 10 to the 5th. The mass, well, of course, it's the same amount of material, so same 100 grams, 0.1 to the kilogram. Plus, you see, I don't write a minus. That's, well, I could have. Same thing. And finally, now ice, losing temperature. So, how much ice? Well, again, same amount. The total amount is the same, 0.1. But for the ice, solid water, the specific heat is different. It's about 2,000 now, joules per kilogram per degree. And now again, well, strictly speaking, it's final minus initial, so -5 minus 0. But we can use the absolute value and the magnitude of this. All we have to do now is just take a calculator and calculate. Again, what is the most important part of the reasoning? This. See, when we talk about forces, we use free-body diagram. When we talk about springs, we use pictures and graphs. When we talk about heat, we use, well, again, a diagram which represents each thermal process, which might happen to each object involved. Okay? So, I'm not going to solve the whole problem. Let's just analyze each process. So what's happening? We have 100 grams of ice. So we have ice, -10 degrees of Celsius. And we mix it up with water. So we have a certain amount of water. Its initial temperature is 10 degrees of Celsius. So, well, first of all, what might happen in general, depending on how much ice or how much water we have? In the end, we may have left with just water. How can that happen? Well, ice should reach the critical temperature, but water still is hot, initial water, so it can release so much heat, so ice might be completely melted, and after that, still get some extra temperature. We made we may end up with just ice left, no water. How might that happen? Well, if we have a large amount of very cold ice and a relatively small amount of not so hot water, so water will be releasing energy. But what might happen? It might cool down to the critical energy, to the critical temperature. Ice might keep absorbing heat, so water might start freezing up, and eventually we might end up with just a piece of ice. And in general, we also may end up with a mixture. In this situation, the final temperature, of course, has to be equal to 0. That only might happen when the initial temperature and the initial amount of ice and water balanced in a certain way. So, in this case, in this problem, we don't have to think about what might happen. We know what has to happen, because the final temperature of the system has to be equal 5 degrees of Celsius. So which case is it? A, B, or C? A. So you see what we have done. First, we placed in our mind the list of all possible situations, final cases. And then we compared with what we have, and we made a choice. This is what is happening in this situation. And now everything is very clear. Of course, what's happening to ice? First, its temperature rises, reaching 0. Then it completely melts. And then starting from 0, this temperature goes up, well, first of all, ice melts. Did I put A? Forgot. Doesn't matter. Not here. Should. So, and then, so basically here what we have left with the pool of cold water, which keeps warming up. And what was happening with that water? It was cooling down, and eventually final temperature was reached 5 degrees. So how many Q's are involved? Q1, Q2, Q3, Q4. Said forward. And now Q1 plus Q2. That's 0 degrees of Celsius. Okay. Plus Q3 plus Q4 has to be equal to 0. Done. There's only one unknown in this equation. The mass of that water, the amount of this water. All other numbers are known. So, and that unknown actually hidden in the last term. So you plug in numbers and you solve it. And what is happening here? Here the final temperature is different. So out of cases A, B, and C, now we should choose a different case. So what's happening here again? Now this cooling down from 10 to 0. Then it's frozen up completely. And then from 10 to 0, now that's an ice. So, and this ice reaching final temperature of -5 degrees of Celsius. That's it. Problem solved. So we have Q1, Q2, Q3, Q4, Q1 plus Q2 plus Q3 plus Q4 equals 0. And so again, we can solve it. Same question. And of course, if you solve it now, you get much smaller amount of water. All right. Now we don't know what will happen. So this is the situation when we have to guess and see if our guess works. If it doesn't work, guess again. What do we guess? Well, again, we have three situations, A, B, C. Remember? So we don't know until we solve the problem. We don't know what is the actual final situation. So we make a guess number one. If it works, fine. If it doesn't, we move on to the guess number two. If it works, fine. If it's not, well, we move on to the guess number three. Eventually, something will work. So what do we have here? Ice. The mass equals 50 grams, 0.05 kilograms. Initial temperature, -20 of Celsius. We have water. The mass equals 400 grams, 0.4 kilograms. Initial temperature, 40 degrees of Celsius. Well, so the natural guess, of course, is to assume that final temperature of the system is positive. So ice melts completely. So that's what we called case A. In this situation, we know that we should have four processes involved: Q1, Q2, Q3, Q4. That's the final temperature, which we don't know. And this is the temperature of the phase transition, 0 Celsius. So Q1 plus Q2 plus Q3 plus Q4 equals 0. Q1, ice warming up. Specific heat of ice, 2,000 joules per kilogram times the mass of the ice, 0.05 kilograms, times the temperature change, 0 minus 20? No. Minus -20. Common mistake, people write up one minus and by some reason don't want to write the second one. These two minuses have completely different natures. This is a difference. This is a negative temperature. That's it. So we're subtracting a negative number. Plus Q2 melting. Latent heat, 3. 1, 2, 1, 2, 3. That's what it is. 300,000 joules per kilogram. And mass, well, same ice, so 0.05. Plus Q3. What is it? Well, first of all, now we don't have ice anymore. Now water is warming up. So first of all, warming up, which means a different equation for Q, Cm delta T. But because it's water, specific heat is 4,000. For this process, what mass should we use? Well, this process describes water, which originally was that ice. So it has to be that mass of the ice which has been melted. And now, times what? Final temperature, we don't know it, minus initial. This water starts warming up from 0 because that was the initial temperature, critical temperature, 0, plus. Last term is related to water, which starts from 40. How much water? Well, first of all, it is water. For the specific heat is 4,000. We had 400 grams, 0.4. We could have used grams. Doesn't matter. when everything is equal to 0, units getting cancelled. Anyway, times what? Temperature change, final temperature minus initial. What was initial? 40. And everything has to be equal to 0. We have one equation to solve for one unknown. Mathematically, it is always solvable. But does it always make sense? Of course not. If our guess was wrong, the mathematical solution will give you a physically impossible answer. You always can solve this equation. Mathematics always works. It's simple. But this answer, it's a number. So it could have been a negative number. What does it mean? Our assumption was wrong. Because everything is based on the assumption that this number is above 0. It could have been 112 or 200 or whatever, above 100. What does it mean? Again, that means our assumption is incorrect. Because again, this temperature has to be lower than 100. So we solve it. And after we have it solved, we have to make a conclusion. So if final temperature is above 0 but less than 100 Celsius, we are done. Done. Yes? How do you know? Did you solve it? Well, you are correct. It's a more strict restriction. If water cools down from 40, it actually has to be equal some number between 0 and 40, not just 100. Even 41 would have been wrong. Good thinking, yes. What? I just repeated what you said. You happy? Me too. That's a very good point, yes. So if this is like coding, writing a program. There's if a fork, done, go home. Or what? Change your assumption. You have 2 left. Now, in this situation, let's just see. So first of all, we can simplify our work significantly. So we can cross out a lot of zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Because divided by 1,000, doesn't change anything. So what do we have here? 2 times 0.5, 0.1, 0.1 times 22. Plus. Now, 0, 0, 0, 0, 3 times 5, 15. Plus 4 times 0.5, 0.2. 0.2 times the final. And here we have 4 times 0.4, 1.6, plus 1.6 times the final, minus, that's 4 times 4, 64, yes, equals 0. So the final will be equal to 64 minus 17 divided by 1.8. Looks like this assumption was correct. It is a positive number, and it is less than 40. Yes?
If the final temperature is 0 degrees, you say it's correct, or should we change it?
If it's exactly 0, yes, you can. It means where is it? Here. It means this process was not happening. That's still possible. We could have changed the number. Instead of 50 grams of ice, we could have used 500 grams of ice. So a huge amount of ice tells us that probably the final state will be just solid piece of ice. So in that case, probably we shouldn't start from assumption A. We should go to assumption B and see if that's going to work. In that situation, what should we say about possible value for the final temperature? Well, it should be either 0 or less than 0, but more than -20. So that's how we check. This is not the only way to approach this problem. We also can calculate how much heat would be needed for each process and to see if we can actually balance them out. Anyway, this always works. This is what I want to do. As we know, everything is made of tiny, tiny particles. We call them molecules. Well, molecules is made of atoms. Atoms made of a nucleus and electrons. We don't know what electrons made of. Nucleus is made of protons and neutrons. Those made of quarks, of subquarks and Higgs bosons and stuff. So, oops, wrong way. This is a model, simple model, simple. This is a simple mechanical model of what we could have seen if we had a very powerful microscope and looking, well, anywhere inside of any piece of metal. As you can see, different particles move differently. Light one moves faster, heavy one moves slower. So we can't say that they have the same speed. No. But what we know now, they all have the same kinetic energy on average. That's why heavy particles move slower and light particles move faster. So when we have any system in thermal equilibrium, any mixture of particles, heavy, light, they all move, and they all have the same average kinetic energy. And this is what absolute zero looks like, no motion. That's what we call 0 Kelvin. And after that, of course, temperature only might go up. So if we warm it up a little, again and again and again. So the temperature is a measure of average kinetic energy. And because, where is it? Even a tiny, well, like a cubic centimeter amount of matter has billions of billions particles inside. We don't use usually regular numbers. Instead of counting grams or kilograms, we count moles. And this stuff you know from chemistry. So if we take a piece of matter which holds 6.02 times 10 to the 23rd particles, that's what we call a mole. And if you know how to use the periodic table, using that periodic table, you can figure out the molar mass of any material. And last slide here. This is the formal definition of absolute temperature. This is what the absolute temperature is. If we look at the kinetic energy, on average, it's just a coefficient between temperature and actual energy. All right. On Friday, I'm going to start from this slide. Thank you very much. Don't forget, today is not Wednesday. Today is Monday. So if you have a lab on Monday, you have it today. If you have a lab on Wednesday, you don't have it today. Okay.
For the previous problem, if our assumption is like the assumption B, mean that it's the combination
No,
of
assumption B is, let me tell you, the assumption B is not an assumption. If we check assumption A and it doesn't work, if we check assumption B, if that doesn't work, that's it.
No, I was just wondering for assumption.
First of all, what do we call ABC? Because
A is above 0. It's actually C. C is at 0.
okay. A is above 0,
Yep.
B is below 0,
Yep.
C is at 0.
Yes.
So again, we never check C first. Doesn't make sense. If we check A, if it doesn't work, we go to B. If it doesn't work, that's the only option left. That's it.
I see.
That's the only option left.
But what if
That's the fastest way.
But what if we do want to represent this
You could have,
assumption?
but
What
in
would
that
the
case,
equation look like?
the equation always looks like this.
But when we
You just didn't have, you wouldn't have this. You would only had 3 Q's, 1, 2, 3,
yes,
right?
but it's like Q2 and Q3 is like both
Yes.
in between this. So
You're asking too many questions. All right, if you want to, the assumption C is actually 3 additional assumptions in it. You made up here, you made up here, or you made up somewhere here, certain amount of ice and certain amount of water.
yep.
So you have to check each individual.
Oh, okay, I see.
Yeah, but we're not going to do something like
Gotcha.
that. It takes too much work. That's it. It's not complicated work, but it's very long work. Checking, you know, so.
But actually, if we got 0 degree for the final temperature, we can it can also fit in both.
If you set final temperature to 0, you can calculate what is the range, the minimum amount of water you should have to end up, and the maximum amount. You can calculate that range, you know.
I see.
And if the actual amount is between, it means you will end up with the mixture. See? So it's all doable, of course. It just requires too much time.
Thank you.
I was just wondering if you got my email about makeup discussions. Just wanted to make sure.
Did you get my email I sent to the class last week?
I think so.
What does it say?
Yeah, so I scheduled it for like this Friday. Is that still
What do you mean?
my makeup discussions
What do you mean you scheduled? To whom?
to Michael or TF? You said that we could schedule it with this TF?
Yes.
Yeah.
So he agreed to be with you.
Yeah.
What's the question?
So I just wanted to make sure that so it will come out this week.
He will, well, you have to meet with Michael, and he will enter your grade.
Okay.
That's it. Yeah.
Can I just unplug the camera?
Yeah, you can unplug everything.
Me neither. Sorry, I wasn't very coherent when I saw you. It is. Oh, you should go out for a ride once you do some summit.
Oh boy. What's that gradient over like a 3 miles or however long?
It's like 6 miles.
It's summit for
Probably
3 miles.
No, it's not that steep for that long. It's awful. From what I gather, I've never
Do people finish it usually?
Yeah.
David did
Those who get off a walk.
I don't know.
If you have a Tom,
You'll do fine. Just do something.
Yeah, my last in the sprite, like I said, is 25.
that's good enough. I'm putting my 15, 30.
I don't know what any of that means. Goodbye.
How do you not know? Okay, my front crankset.
No, you
I
know.
just learned how to use shifters last like December.
Yahoo.
I was like, what is that?
No. Alright,
Today?
kids. We'll see you later.
All set.